Hey everybody! So today's video, in short, is kinda long. Around 3 hours to be exact. And that's because it is a crash course in the entire Python programming language. Which means 3 hours is actually kind of short if you think about it. But that's because this crash course covers just the parts of Python you need to know in order to start applying Python to data analysis, using libraries like Pandas. My goal is not to turn you into a software engineer here. Data is my thing, not web apps or shiny user interfaces. So instead of making you slog through a bunch of obscure Python syntax you'd almost never use as a data analyst, I've kept a ruthless focus on the minimum Python syntax you'll need to get started. No more, no less. Now, as to actually analyzing data with Python, I plan to post another video with an introduction to that soon. But for comprehensive end-to-end coverage on how to transform and analyze data in just about every conceivable way with Python, I highly recommend checking out my Python/Pandas bootcamp on Udemy. I may be just a bit biased, but I personally think it's a pretty amazing course. I've included a link to the course in the description for this video, which will let you buy it at a discounted price. You're welcome in advance. Okay, so with that shameless but sincere plug out of the way, let's get right to it. We'll begin at the beginning by digging into what exactly programming even is up next. First, let's consider where computers fit into the bigger picture of society. So as humans, we have the ability to apply creativity, imagination, and intuition to solve problems. Things no computer can match, at least for now. But computers are also much faster and less error-prone at certain kinds of tasks than we are. And that's where programming comes in. Programming is all about humans telling computers what to do, using a type of language called a programming language that a computer can understand. For example, let's say we want to count the number of times a particular word appears in a text file. We can do this in an automated fashion by using a programming language to explain to a computer how to perform this task step by step. In a sense, these instructions we write in a programming language, which are commonly referred to as code, hence all those things you've heard about coding and learning to code, are quite similar to the kind of normal writing we do every day, like writing an email to a colleague to make a specific request. And just like an email is a group of sentences assembled to convey a certain message, a batch of code written to accomplish a specific purpose is called a program. But before we can code our own programs, we first need to learn the language, at least a little of it. Actually, you'll be surprised at how much we'll be able to accomplish early in the course with just a smidgen of code. Now, there are lots of programming languages out there, but in this course we'll be using Python, which is a popular and widely used programming language that is especially well suited for data analysis tasks. Now, like all other programming languages, Python has a vocabulary consisting of special reserved words that we'll use as the building blocks of our code. And to put Python, or any other language, to work for us, we'll need to learn the basics of how to combine and arrange these words in a way that describes what we want the computer to do. This arrangement is called the syntax of the language. Now, for those of you who have ever attempted to learn a second human language, this may sound daunting, but fear not. Communication with a computer is much simpler and more structured than communication between humans. And we only need to learn a very small subset of a programming language to do some really cool things with it. So speaking of those cool things, here are some of the broad categories of things we can ask for a computer's help with. Input. Basically, getting data from the outside world, such as reading from a file or receiving input from a user. Then there's output. Displaying the results of executing programming code on a screen, or storing those results in a file. Conditional execution. Executing or not executing some programming code based on specified logical conditions. Repeated execution. Performing a set of instructions to the computer repeatedly, usually with some variation. And finally, reuse. Giving a set of instructions a name and reusing them throughout the program. Now, throughout this course, we'll revisit these forms of communication and their syntax as needed for different data analysis techniques. Remember, while this is fundamentally a course about data analysis with Python, you will also learn the fundamentals of the Python language itself along the way. Which begs the question, why choose Python in particular for data analysis? Well, for one thing, Python has a very straightforward and intuitive syntax, which reads quite a bit like a human language, and can often be followed, at least somewhat, by people who haven't even programmed before. Python can also be applied to a wide range of applications aside from data analysis, including web development and machine learning. So you can actually use what you've learned in this course as a springboard into entirely different domains and career paths. Further, Python is an extremely popular language, which results in the creation of many specialized Python libraries, basically collections of pre-written Python code that extend the language's capabilities in accomplishing certain kinds of tasks more easily. In fact, most of our work in this course will involve one or more of these libraries. So one potential downside to Python is that it's what's called an interpreted language, which means it needs to be translated or compiled by another program before it can be run on a computer. Now, we don't have to worry about doing any of that translating ourselves, fortunately, but this added step in the overall process can make Python slower than non-interpreted languages. However, the most expensive aspect of writing software is almost always the time it takes to create it. And time is money, right? So a language that allows people to solve problems faster is worth its virtual weight in gold. Okay, so now that we have a general understanding of what programming languages are and why we use them, up next we'll explore where all that programming code actually goes. That is, the environment, or at least an environment, where we can do programming. I'll see you then. So as programmers, we need a place to write and run our code. This often involves a specialized text editor called an IDE, short for Interactive Development Environment, that also compiles our code for the computer and typically includes other useful functionality for programmers as well. In the context of data analysis and data science, the focus of this course, the industry standard IDE for writing Python is a Jupyter Notebook. Jupyter Notebooks are interactive, web-based tools that allow you to combine code, computational output, explanatory text, and even multimedia resources in a single document. And they are optimized for working with and analyzing data. One option for using Jupyter Notebooks is to install Python and the Jupyter Notebook on your own computer. However, as the problems you tackle become more complex, you may need to install more and more tools and extensions to Python, which can be an issue depending on the capabilities of your computer. Additionally, the datasets you work with as a data analyst can be very large, which can also be a problem for personal computers. A great solution to these issues is to use cloud-based computing, which involves using servers in the cloud to perform heavy-duty analytical tasks. Cloud-based computing is often the best option because it has almost limitless computing power, and many services offer free tiers depending on how heavily you use them. One of the best cloud-based computing services is Google's Colab, a cloud-based Jupyter notebook. Now the great news is, since Colab runs in the cloud, you don't need to install anything on your computer. Now to use Colab, you'll first need to set up a Google account. If you have a Gmail address, congrats, you already have a Google account and you're ready to go. Otherwise, just follow these steps to create a free Google account. So first up, we just navigate to google.com, and then up here at the top right, we hit this Gmail button. And then once we're here, we click this Create an Account button. From here, you'll follow a series of very simple steps, and then you'll have your free account set up in seconds. So now that you have a Google account, whether you did this before the video or not, it's time to jump into Colab to take our first swing at writing some actual Python code. So to do that, our next step will be to navigate to colab.research.google.com, which takes us to the site you see here. Now, when you first navigate to this page, by default, you'll see a pop-up window with a list of Colab notebooks you've recently worked on. Now, you probably don't have any just yet, and we want to create our own brand new notebook in any case, so instead of clicking any of these files here, I'll instead hit the New Notebook link at the bottom of the window. Now that our new blank Colab notebook has been created, it's worth noting that you can also create a new notebook directly from an existing notebook by hitting File and then New Notebook. So if you look closely at this blank Jupyter notebook that was just created for us, you'll see that the cursor is flashing in this wide rectangular widget right beneath the menu. That widget is called a cell. So cells are the fundamental building blocks of a Jupyter notebook, where you'll write the discrete chunks of code that will process, analyze, and visualize your data step by step. But before we get to all that, let's start with just about the simplest task imaginable, writing out the phrase "Hello World" to the screen. Now, if you didn't already know, printing "Hello World" or variants thereof is kind of a time-honored rite of passage for aspiring programmers. So we can perform this simple task using Python's print function. Now, if you have it programmed before, don't worry too much about a dictionary perfect definition of what a function means in programmer speak just yet. Suffice it to say, it's a pre-built piece of functionality built right into the programming language that allows us to perform some task without knowing exactly how that task is being executed at a lower level. In this case, we will be telling Python to print a piece of text, and it will hopefully oblige us by doing just that. So to start, we'll type the name of the function, print, followed by a pair of parentheses. When you're using a function in Python, parentheses always come after the function name. So let's go ahead and do that. Next, in between the parentheses, we'll just type the text we want to print to the screen, nested inside a pair of quotation marks. We'll dig deeper into why those quotation marks are necessary later on, but for now, suffice it to say that when you're working with strings of text, as opposed to things like numbers, in Python code, those strings of text need to be wrapped in quotation marks. So I'll type my double quotation marks, and then inside of those, type our message, "Hello World." Finally, to execute this code, and to execute code in any cell of a Jupyter notebook, you simply hit this little play button here to the left of the cell. And after waiting a few seconds for our notebook to connect to that server in the cloud that's actually running our code, we see that our message, hello world, was in fact printed to the screen. But we don't have to stop here. We can actually create a new cell in the notebook, or really as many new cells as we want, by hitting this plus code button directly above our first cell. And as you can see, that creates another new cell in the notebook. So in this one, instead of printing hello world, I'll print howdy earth. Now instead of going to all that trouble of typing the whole thing out, I'll just copy my code from this first cell and then paste it into the second cell and simply change the message inside of my print function. So again, I'll change that to howdy earth and then run that cell. And there's our new message. Now, if we decide these two messages are a little bit redundant and we don't need both of them, we can actually delete either one of these cells by simply clicking it to select it and then clicking this little trash can icon that appears directly above the cell. Incidentally, this set of icons that appears above and to the right of a cell when you select it is a kind of toolbar that offers commands specific to that cell. So to delete our first cell that prints hello world, I'll just hit this little trash can icon, and now it's gone. So now that we've actually done something in our Jupyter Notebook, how do we save our work? So notebooks are saved as files with the .ipynb extension. You can save, close, and reopen notebooks in Colab just like you would any other type of file in any other program, like Microsoft Word or Google Docs, for example. By default, notebooks are saved to Google Drive, Google's built-in cloud storage service for storing files in the cloud, which you get for free with a Google account. But you can also download them to your computer or even save them to GitHub, a platform that allows you to store your code and share it with other developers. Additionally, you can save notebooks in different formats, perhaps most helpfully PDF files. But as I said, by default, these files are saved to Google Drive. And in fact, this file has already been saved there. So our first step should be to actually rename it to something meaningful. Say, Howdy Earth for lack of creative inspiration, which we can do by simply changing the text up here at the top left. So I'll actually just copy this text from our print message and then paste over Untitled 1 and hit Enter to lock that change in. And just like that, our Colab notebook has been renamed. But now the question remains, where exactly can we find our file in Google Drive after we've created it? Well, let's find out by hitting File and then Locate in Drive. And there we are. If you look at the breadcrumbs right below the menu here, you'll see that the file is located in a folder called Colab Notebooks, which was created for us automatically, that is a subfolder of the root folder in Google Drive itself. This is where all new notebooks you create in Colab will be saved by default. But sometimes, especially after we've created a lot of notebooks, as we will have by the end of this course, it can be useful to further organize this Colab Notebooks folder into subfolders. To do this, we can simply create a new folder within this folder by hitting New, and then New Folder, and then assigning a name to our new folder. I'll go with Programming Basics, and then hit Create. And now we can simply click our Hello World notebook to select it, and then, holding down our mouse key, drag it right into the new folder. And if we double-click our new folder to open it, there's our file. So now we can file away all those notebooks we'll be creating into as many folders and subfolders as we like. Now, as an aside, it's also worth noting that you can move files directly from the Jupyter Notebook menu via File and Move. So going back to our Colab file, if I hit File and then Move, I have the option here of selecting any old folder in Google Drive to move this Colab notebook to. Now, similarly, you can easily add a new Colab notebook to folders anywhere in Google Drive, not just the dedicated Colab Notebooks folder. For example, if I navigate to another random folder in my drive, and then right-click, if I roll down this list of options to More, and hover over that, and then scroll through, we see that Google Colaboratory is one of the types of new files I can create in this folder. Okay, so now we know what programming is, and we also know where we're going to be doing our programming for the rest of the course. So up next, we're going to take our first real foray into the nuts and bolts of programming, with values and types. I'll see you then. So now that we've gotten past the obligatory Hello World demo, it's time to start laying the foundation for real programming in Python. And the building blocks for pretty much any computer program are individual pieces of data, such as numbers or strings of text characters like a person's name, which are typically referred to as values. And every value in Python has a type, which is basically a classification for what, well, type of data it is. For example, a number with no decimal component is called an integer. The official name for this data type in Python is int. Conversely, a number with a decimal point is referred to as a floating point number, or just a float in the parlance of Python. And then there is the string data type, represented as str in Python, which encompasses sequences or strings of characters. These are commonly names of things, in which case the characters are mostly letters, but they can also consist of numbers. Think of an identification number, for example. You probably wouldn't try to perform a mathematical operation on this kind of number, like multiplying it by 2, and yet it may consist entirely of numeric digits. In fact, as we'll see, a value's type greatly impacts the kind of programming operations, like multiplication for example, we can perform on it. It's worth noting that there are many other data types in Python, many of which we'll encounter throughout the rest of the course. But these three are arguably the most foundational and the most common. So now, before we go, let's do some very basic programming with these different types of data. So here in the example notebook, I'll first print an example of an integer, the number 42, which some contend is the meaning of life itself. So I'll go ahead and print that in our first cell, and then hit Control-Enter to run that cell. Okay, I don't feel especially enlightened even after printing 42. So I think I'll move on to printing a floating point number, 123.45. So I'll hit my plus code button here to add a new cell, and then simply print 123.45. And then Control-Enter to run it. Pretty much the same thing. And you'll find that for many, but not all purposes in Python, integers and floating point numbers can be handled the same way. Now, where things get more interesting is with strings. So let's try to print a string. Say the sentence, "This is a string." So again, I'll create a new cell and add a print function, and then just type that sentence in between the parentheses. And run it. And right away, we get our very first error, which I can assure you is not a bad thing. Professional programmers get errors in their code all the time. But what separates the pros from everybody else is how they respond to these errors. By calmly reading the error message, reviewing the problematic code, researching the issue if needed, and finally fixing the code. Not, as you might imagine, by losing confidence, getting frustrated, and possibly sending your computer through the nearest window. Although this can be tempting at times, admittedly. So this error is pointing to the text we fed the print function and telling us we used invalid syntax, which is just a fancy way of saying we didn't follow the rules of the Python language, much like if you forgot to put a period at the end of a sentence in the English language. So what's wrong with our syntax? Well, if you recall back to when we printed "Hello World" in the last video, we wrapped the characters of that phrase in quotation marks. And that, as it turns out, is how we tell Python that what we're referencing is actual data, a text string, and not the name of some feature or function within the Python language itself. For example, imagine if we tried to print the word print. Python wouldn't know whether we're talking about the word print or the Python print function. This sort of confusion isn't a problem with numbers like 42 and 123.45. After all, Python probably isn't going to have some built-in function or reserved word called 123.45. So quotes aren't necessary for numbers. So now if we add those quotation marks around our sentence here and then rerun the cell, the correct value prints to the screen. Now it's worth noting that you can actually use single quotes or double quotes to mark the beginning or end of a string. So for example, I can replace our double quotes here with single quotes, rerun our cell, and it works just the same as before. But if you want to include a single quote in the body of your string value, like for example, in a contraction like the word I'm, you'll need to stick with double quotes. So to show you what I mean, I'll change our string here from "this is a string" to "I'm a string." And then I'll rerun that. And once again, we get that invalid syntax error. Our code confused Python because Python thinks that second single quote after the letter I represents the end of the string. But then we have even more characters and another orphan single quote at the very end. But now if I change those single quotes that are bracketing our text string to double quotes, and then rerun the cell, now it works just fine. And as you might expect, this same principle works in reverse too. If your string includes a double quote, you'll want to wrap your string in single quotes. Now finally, let's consider what happens when you print a number, almost like we did before, but wrapped in quotes. So I'll add a new cell, and then simply print 11.11, but wrapped in quotes. Now the output looks the same as when we printed numbers earlier, but behind the scenes there's a crucial difference. Because of those quotes, Python looks at this number the same way as it might look at a person's name. To revisit our earlier example, this kind of string is like an ID number, a sequence of characters that just happen to be numeric, as opposed to an actual number you can perform calculations on. We'll dig deeper into how to determine data types programmatically with Python, as well as the kind of programming operations we can perform on each data type later on. Alright, with a deeper understanding of the basic building blocks of a Python program, we're ready to move on to learning about functions, which will supercharge your ability to do cool and interesting things in Python. That's up next. I'll see you then. So we've been able to perform some very basic programming operations up to this point, but to do truly useful and interesting things, we're going to need to take advantage of more of Python's built-in functionality. What functionality, you say? Well, functions. So a function is just a named chunk of code that we can invoke on demand that performs some specific task, in kind of the same way that your phone has a camera function that allows it to take pictures, or an email function that allows you to send emails. But in addition to performing tasks, functions can also return values, as we'll see in a moment. So to invoke or call a function in code, all we need to do is type the name of the function followed by a pair of parentheses. Some functions, but not all, will also need us to supply one or more pieces of information to them that are then used by the function to generate its output. These pieces of information are called arguments, and we pass them to the function by typing them in between the parentheses after the function name, separated by commas. Then, when we run the code, whatever function that function performs will be executed. This functionality, okay, I'll stop with the function puns for now, can range from relatively mundane actions to some seriously impressive stuff. We'll see examples of the latter later on when we dive into Pandas. For example, let's say you want to find out what data type a certain value is. Python has a built-in function called type that can help with this. All you have to do is pass in the value you want to check. So for example, I'll print the output of feeding the number 1, 2, 3, 4, 5 into the type function. So first I type out my print function, and then inside of the print function, I'll use my type function, and then as the argument to my type function, I'll type 1, 2, 3, 4, 5, and then if I run my cell, we see, as expected, that the type of the number 12,345 is int. And then for another example, I'll also print the type of the text string hello world in another cell. So I'll go ahead and paste in our print code from the first cell. And instead of a number as the argument to our type function, I'll just type that text string hello world. And now when I run that, we see that the class or type of that particular piece of data is string. Again, just as we'd expect. So our type function is clearly the type of function that returns a value that happens to be the data type of the value we pass to it. But print, which we've been using all along, is also a function in which the argument we pass in between the parentheses after the function name is just whatever we tell it to print. But you can think of print as more of a doer function that performs the action of printing some text to the screen versus type, which is a function that returns a value. Now it's worth noting that our code here is an example of nesting functions, which means using the output of one function as the input, or more specifically an argument, to another function. Here, the output of the type function is being passed into the print function as an argument. This kind of nesting is quite common in the wild, as it's a convenient way to execute a series of actions or transformations on a piece of data. Now at this point, you might be wondering if you can create your own functions in Python. The answer is yes, you absolutely can. But Python has so many useful functions built right in that you can go far without rolling your own, so to speak. So for now, we're going to focus on those. So we've used the type function to determine the type of a piece of data. But what if we want to convert a value from one data type to another? Well, Python has functions for that too. For example, let's say we have a decimal number, or in Python speak, a floating point number, but we want to convert it to an integer. Well, we can use Python's built-in int function to do this. So let's say I want to convert the value 123.45 to an integer. So in a new cell here, I'll just print the output of the int function, and then I'll pass into that int function the value 123.45. And then running our cell, we see that that value has been converted to an integer, 123. Basically, that decimal component of the number has been clipped off. Now, conversely, we can also use Python's built-in float function to convert an integer or a string to a float value. So let's say I want to convert 123 from an integer to a float. Well, I'll grab our code from the previous example and paste that into a new code cell. And then I'll just change the 123.45 to just 123. And then instead of the int function, I'll use the float function. And now, running our cell, even though the value returned is technically the same as the argument we passed to the float function, it now has a decimal component, of course, of simply 0.0. Similarly, we can convert a text string that happens to consist of numeric characters to a float as well, or an int for that matter. So in a new code cell, I'll replicate our code from the last example, but now I'll wrap that 123 in quotes to make it a text string. And now running that, the float function is able to convert that text string into an actual floating point number just as easily as it was the integer. Now keep in mind that these functions only work when the data you're trying to convert is actually compatible with the data type you are converting it to. For example, if I try to convert the string howdy earth to an int, so I'll add a new cell here, and then I'll print the output of passing the string howdy earth to the int function. And then if I run that, Python gets upset since there's just no scenario in which that string could be interpreted as a number. Now, as another example of one of Python's data conversion functions, the string function, which converts inputs to strings, is a bit more generous than the int function or the float function, since basically any sequence of characters can be treated as a string. For example, I can easily convert the number 12345 to a string consisting of the characters 1, 2, 3, 4, and 5. So to see that, I'll add another new cell, and then I'll print the output of feeding the number 1, 2, 3, 4, 5 to the string function, which of course is spelled str. Now there's nothing about the output of the code we just ran that proves to us that this is actually a string value. But if we wrap the output of the string function here in a type function, that may be enough to prove it to us. So let's go ahead and do that. And now we see that if we feed a number to the string function and then put that output into the type function, the type function returns a string. So clearly that number was in fact converted to a string. Now it's worth pointing out here that we're now nesting 3 functions deep: the string function inside the type function and the type function inside the print function. Now we can actually nest as many functions inside of other functions as we want, but it's best not to go too crazy with nesting just for the sake of readability. Now it's also important to understand that these functions aren't all of the type conversion functions that Python has to offer. They're just 3 of the most common. To see a comprehensive list of those functions, as with pretty much anything else you might need to look up, but definitely don't need to memorize, I would highly suggest referring to the Python documentation. Okay, now that we've seen how Python's built-in functions can perform certain operations on our data more or less for free, up next, we'll dive into performing our own custom operations on data with expressions. I'll see you then. So now that we know how to use functions to take advantage of some of Python's built-in abilities, let's look at how to create our own useful custom functionality in Python using expressions. So an expression is just a combination of values and operators that Python can evaluate. For example, 2 plus 2 is an expression that evaluates to 4. In this case, the operator is the plus sign that performs the addition operation on the values 2 and 2. Operations are just actions that we can perform on values. In Python, we can perform all kinds of operations, like addition, subtraction, multiplication, and division, just to name a very few. The specific operations that are available for us to perform on a piece of data depend on the type of that data. For example, if we have a number, we can add, subtract, multiply, or divide it. If on the other hand we have a string, we can concatenate it with another string, but we can't perform math on it. So now that we understand the basics, let's kick things off by diving into some examples of numeric expressions in Python. First up is addition, which we just saw an example of. 3 plus 2 equals 5, which shouldn't be too controversial. Pretty straightforward stuff. Subtraction is similarly straightforward, using the minus sign operator we're all familiar with. Things get slightly more interesting with multiplication, where Python uses an asterisk instead of the standard X you might be accustomed to as the operator. For division, on the other hand, our operator in Python is the /, as we see here. Now there's actually another flavor of division in Python called integer division, which uses not one, but 2 / as its operator. The difference is, integer division returns just the whole number result of the division without the decimal. For example, 3 /2 returns 1, not 1.5. This sort of division can be useful in certain situations, so it's good to keep in mind. Next up, we have the somewhat exotic and futuristic sounding modulo operation, which uses a % sign for its operator. The modulo operation gives us just the remainder of a division operation. So using 3 and 2 as our inputs once again, we get 1 as the result, just like in our integer division example, but for a different reason. In this case, 2 divides into 3 completely just one time, leaving a remainder of 1. Now you might be wondering what the heck this could ever be used for. Well, for one thing, it can tell us if a number is cleanly divisible by another. That is to say, there's no remainder when we perform division. In this case, modulo returns a result of 0, meaning no remainder. That can be handy for things like testing whether a number is even or odd. For example, if I perform the operation 142 modulo 2, I would get a result of 0, meaning that 2 divides cleanly into 142, which in turn means 142 is even. If we get anything other than 0 as the result, using 2 as the second input to the expression, we know that the first input is odd. If we do 141 modulo 2, we get 1. So we know that 141 is odd. And frankly, 141 is kind of a weird number, am I right? And that cataclysmically awful joke brings us to exponentiation, which is just raising one number to the power of another. In Python, we use a double asterisk for this particular operation. So for example, 3 *2, that is 3 raised to the second power, which we could also refer to as 3 squared, returns 9. Basically, we're just multiplying the first input by itself, the number of times specified by the second input. Now 3 times 3 is 9, of course. But if we were to change this expression to 3 *3, now our result would be 27, which is what you get when you multiply 3 by 3 3 times. Now, when we're piecing together numeric expressions in Python, it's very important to keep order of operations in mind. In other words, the order in which Python executes these operations if we chain together several of them in a single expression. This order pretty much follows what you no doubt learned about and then worked hard to forget, if you're like me, in high school math. An easy-ish way to remember this order is the acronym PEMDAS, which stands for parentheses, exponents, multiplication, and division, all performed left to right, then addition and subtraction, also performed left to right. The parentheses piece is especially important because it allows us to control the order in which these operations are executed just by wrapping certain sub-expressions, if you will, in parentheses. As you'll see, this can have a huge impact on the result of our expressions. For example, if we use the expression 3 plus 2 times 4 in code, left to its own devices, Python will give us a result of 11. That's because it will multiply 2 times 4 first, rather than adding it to 3, due to multiplication being higher on the old PEMDAS ladder than addition. Then it will add the result of 8 to our first input, 3. What if, however, we want to add 3 and 2 first, and then multiply the result by 4? Well, we can force Python to do this simply by wrapping the sub-expression 3 plus 2 in parentheses. This gives us a very different outcome of 20, underlining just how much order of operations matters. Now, the PEMDAS acronym is handy for remembering the proper order of operations, but not everyone, including people who may someday have to review your Python code, may be as familiar with it as you now are. As such, I generally recommend using parentheses to specify which expressions in your code you want to be evaluated first, even if order of operations would have taken care of that for us anyway. So in our first example here, I'd probably put parentheses around 2 times 4, even though it won't change the output in that case. It makes the intent of my code clear, to myself and others, and makes sure that I don't make a critical math error because I haven't had my coffee yet and forgot my handy PEMDAS acronym. Now before we go, let's give expressions involving string data some love. After all, boring old numbers shouldn't have all the fun. First up, let's look at text addition, more commonly known as concatenation, which really just means piecing strings together. Not surprisingly, given the additive nature of this operation, the familiar old plus sign is our operator here. Now, while the concept is straightforward, note that our example here actually involves adding 3 strings, the second of which just looks like an empty pair of quotes. But they're not entirely empty. There's actually a space, which is technically a text character just like any other, in between those quotes. We need to concatenate that in between the other 2 strings, so howdy and earth are separated by a space, and not just all one word. An equally valid approach would be to simply throw the space in at the end of howdy or at the beginning of earth. Totally your call, but the first option has the benefit of being more clear and explicit, which is often a good thing. Now the last, and probably coolest operation we'll look at, is text multiplication. That's right, you can actually multiply text strings. Not by other strings, mind you. Hello times world obviously doesn't make a lot of sense. But if we multiply, say the word hi by the number 3, we get back a text string consisting of hi repeated 3 times, back to back. Pretty cool. Now, math with text strings obviously has its limitations. Try dividing a word by a number if you really want to make Python angry, for example. But just addition/concatenation and multiplication can let us do some pretty handy things with text data. Okay, so this has already been entirely too many slides for my liking. So up next, let's dive right in to actually coding up some expressions in a Colab notebook. See you then. It's time to take what we learned about Python expressions and operations in the last video and apply it by writing some actual code. In a Colab notebook, of course. First things first, let's talk about printing the output of an expression. Now we've already seen how we can use Python's print function to, well, print values to the screen. Well, likewise, we can also use it to print the result of an expression. For example, let's say we want to print the result of an integer division expression. Say 7 integer divided by 2. So I'll go ahead and punch that into a Colab cell. And then run that. And as we'd expect, we get 3, not 3.5, since 2 goes into 7 3 whole times, not accounting for any remainder. But here's the thing. We don't actually always need to use the print function to print the output of an expression in a Jupyter notebook. That's because the output of the last line of code in a given cell is printed automatically when the cell is run. So in other words, if there's only one line of code in the cell, we only need to run the cell to see the output. No print function required. For example, now let's say we want to run an exponentiation expression. Say 2 to the third power. We can just write the expression in its own cell like this. And then running that, the output we expected, you did expect 8, right? Is printed automatically without using an actual print function. Pretty cool, right? But now let's say we have multiple lines of code in a single cell. In this case, by default, only the output of the last line of code will be printed to the screen. For example, let's say we have a cell with 2 expressions on separate lines, one that performs text concatenation and another that performs text multiplication. I'll go ahead and put that together real quick. So my first line of code will concatenate the text string, "the meaning of life is," with the number 42. Wrapped in quotes, of course, so Python knows we mean 42 as a string and not as a number. Then, my second line of code will perform text multiplication, multiplying the string 42 by the number 8. Now if we run this, only the output of our text multiplication expression is printed. But what if we want to view the output of multiple lines of code in a single cell? Well, all you need to do is explicitly print the result of the other lines of code besides the last line. So if I wrap our first expression here in a print function and then rerun the cell, there we have it. Now the results of both expressions are displayed. Now just to reiterate something we've touched on over the last few videos, by wrapping the number 42 in double quotes in both of these examples, I am explicitly telling Python to treat it as a text string, no different than hello, world, or your name, and not a number. Therefore, when we multiply 42 by 8, instead of getting, wait for it, 336? Is that right? We get a text string consisting of 42 repeated back to back 8 times. Perhaps a little less intuitive than repeating a word a certain number of times, but the principle is the same. And it's certainly less annoying than printing something like, "hey" in all caps over and over again. But I'd never do that to you. Sorry, I just couldn't resist. Okay, probably better wrap this one up before I completely wear out my welcome. So up next, we'll look at a feature of Python, and pretty much any other programming language, that will allow us to take our expressions to the next level. Variables. I'll see you then. So the expressions we covered in the last video may not have seemed much different than something you would crunch out in a spreadsheet, or even on a piece of paper. We were essentially using Python as a glorified, supercharged calculator. But now it's time to get into more, well, programmery stuff. And maybe the best place to start is with variables. So that, of course, begs the question, what the heck are variables? Simply put, variables are like little named storage boxes for pieces of data. Data like the values we've been working with so far, such as numbers and text strings, for example. You simply give a variable a name, and then you can store a value of some kind, any kind really, inside of it. The great thing about variables is that you can define them once and then simply reference the variable name, not the exact value stored in it, in the rest of your code. This prevents you from needing to remember the exact value you stored in the variable every time you use it, which has the added benefit of ensuring that you don't accidentally use the wrong number somewhere in your code because you misremembered the original value. As you might imagine, this feature comes in especially handy when you need to reuse the same value multiple times in your code. Now, another incredibly useful feature of variables is that we can overwrite them with new values. After all, variables should be able to vary. This makes our programs more flexible, since all we need to do is change the value of the variable in one place, and that new value automatically updates anywhere else the variable is referenced. Now, don't worry if you can't see the value of this just yet. It'll make more sense once we walk through some examples. So how to create a variable in Python? It's actually super easy. All you have to do is give your variable a name, and then use the equal sign to assign it a value. In programmer speak, this is called declaring a variable. So for example, let's say you wanted to create a variable called myVar and store the number 10 inside of it. You would just write myVar equals 10, and boom, you've got yourself a variable. So that's enough slides for one video. Now let's get our hands dirty with some live code. So in a new Colab Notebook cell, I'll create a variable, once again called myVar, and assign it the value of 42. Then I'll use the print function to display the value of my variable on the screen. So I'll start off by simply typing myVar equals 42. And then on the next line of code, I'll print the value stored in myVar. And now if I run this, there we go. When we run the cell, it prints out the number 42, which was the value stored in our variable myVar. But we actually don't even need the print function to display the value stored inside the variable. Remember how the output of the last line of code in a cell is automatically displayed on the screen when we run the cell? Well, if we just type the variable name on the second line here and not even use the print function, so I'll go ahead and get rid of that closing parenthesis and then delete everything before the name of our variable, and then rerun the cell, it still displays the value of myVar without us having to use the print function. And our program will also remember the value of the variable in other cells too, as long as those cells come after the cell where we created/declared the variable. So if I create another cell and just type myVar in it, and then run that cell, the same value appears. This is how we can declare a variable once and then use it throughout our notebook and/or program. Now let's say we want to do something a little more interesting with variables. For one thing, we can use them as inputs to expressions, just like we would with regular old values like numbers and text strings. For example, let's say we want to divide our myVar variable by 2. So all I have to do is type myVar divided by 2 in a new cell. And then if I run that, there's our answer, lucky number 21. Now we can also use variables as inputs to text-based expressions. So let's say we have a variable called firstName that stores the string John, and also a variable called lastName that stores the string Doe. Now if we want to combine those two variables to create a full name, we can do it like this. So creating a new cell. In this cell, I'll start typing the name of our first name variable. And if we pause after typing the first 3 letters of the name of that variable, we actually see the full name of our variable appear first in this list of items that all begin with FI. Now, this is a feature in a Colab notebook, and it's also found in many other programming environments, commonly referred to as IntelliSense or code completion. What Colab is doing for us here is guessing what we're trying to type based on the first few letters we typed. And because that variable has already been declared and Colab is already aware of it, when we start typing the name of the variable, it appears as an option for us to select without us actually having to type out the whole name of the variable, which, if you're a terrible typist like me, is a terrific advantage. So what I'll do is make sure that first name is selected in this list, which it is by default because it's first in the list, but even if it wasn't, I could use the arrow keys to navigate up and down to select it, and then hit the tab key to lock it in. And next, I'll concatenate a space that will go in between our names. And lastly, I'll tack on our last name variable, which I will also let Colab's code completion help me out with. And now if I run that, you'll see that we actually get an error. And that's because we hadn't first run the cell that declared our first name and last name variables. So now our cell that references those variables doesn't know what we're talking about because as far as Colab is concerned, they don't exist. So let's first run that previous cell. And now running our last cell one more time, there's the output we were looking for. Now, alternatively, we can even store this full name in its own variable, which I'll do in a new cell. So creating that cell, I'll copy our expression here, and then in this new cell, I'll declare a variable called full name, and then set it equal to the expression in the previous cell. And then on the next line of code, I'll simply type out the name of our full name variable. And now if I run this, you'll see that John Doe prints once again based on the value that we stored in that full name variable. Now, as I alluded to earlier, the values inside of variables can be changed or overwritten. So let's say we want to change the value of first name from John to Jane. We can simply update the original variable declaration, first name equals John, to first name equals Jane, and then rerun that cell. And now if we rerun the subsequent cells, you'll see that the output changes to reflect the new value stored in the first name variable. Now in this case, we simply changed the variable declaration. But again, variables can also be overwritten after their original declaration. So if I create a new cell in between the two cells that reference the first name variable, which I can do by clicking the first of those cells here and then hitting new code, which will insert a new cell after this one. And then if I type first name equals John, this will effectively overwrite the original value stored in that variable, but only after the line of code where I overwrote the original value. So now the first name variable holds the value Jane from the time that variable is declared all the way until we get to this cell, and then it holds the value John after that. Now, just to prove that to you, I'll rerun all the cells in our notebook, which we can actually do in one fell swoop by hitting run time and then run all. And there we have it. The first cell prints Jane Doe, then after the cell in which we overwrote the first name variable, John Doe is printed instead. Now it's important to note here that Python is what's known as a dynamically typed language. This means that you don't have to specify what data type you want to store in a variable when you create it. Python will just figure it out for you based on the value you assign to the variable. For example, let's say we have a variable called dynamic, and we want to store the string hello world inside of it. Easy enough for us by now, I think. So I'll just create a new cell and then declare a variable called dynamic and set that equal to the text string hello world. And then run that. But now let's say we want to change the value of dynamic from a string to a number. So all we actually need to do is overwrite the variable just like we did before. So I'll go ahead and do that in a new cell. And here I'll just say dynamic equals 123.45 and then run that. Easy peasy. Python doesn't fuss at us one bit. And we didn't have to do anything special to tell Python that we wanted to change the data type of our variable. It simply figured that part out for us. However, it's important to note that changing the data type of a variable can cause problems if you're not careful. So let's say we want to see the updated value of our dynamic variable divided by 67. So if we enter that expression in a new cell, and then run that, so far, so good. But if, in the new line of code where we change the variable's value to 123.45, we update it to the string what's up Earth instead, and then run that cell, and then the cell below it, whoops, we get an error. And that's because we're now trying to divide a bunch of letters by a number, which doesn't make any sense, either to us or to Python. So this is just one example of how changing the type of data stored in a variable can result in unexpected issues. As such, it's important to be mindful of the data types of your variables, especially if you're using them in expressions. All right, so tricky issues with changing data types aside, using variables turns out to be pretty daggone straightforward. But what's surprisingly not quite as straightforward as you'd expect is naming variables. That's right, just figuring out what name to give those little pieces of data. That topic deserves its own video, which as it happens is coming up next. I'll see you then. So one thing you'll discover as you get more experience writing code is that in programming, naming things is surprisingly hard. Every name you choose for a thing in your code represents a decision you have to make. And those decisions can be harder than you might think, because as it turns out, the names you choose for things matter. Now, since variables are just names for pieces of data, and we tend to work with variables a lot when programming, we will find ourselves deciding on names for variables all the time. As such, it's helpful to have a good understanding of both the hard and fast rules, as well as some best practices and guidelines for naming variables in Python. Let's start off with those hard and fast rules. So first of all, variables can only contain letters, numbers, and underscores. But crucially, they can't start with a number. Variables are also case sensitive, meaning my variable, all lowercase, is treated as a different value from my variable with the first letters of each word capitalized. Now with that said, to avoid confusion, I'd strongly recommend not putting this particular feature to the test by having multiple variable names that are identical except for their capitalization. Now these rules still leave you with a lot of latitude to decide how variables should be named. A little too much in my opinion. You see, you'll have to make lots of these little decisions as you code, and if you don't have a system for deciding how to name your variables, then time spent making those decisions can add up. To solve for this, I recommend following a naming convention for variables that will absolve you of some of this decision making. So two popular naming conventions in programming are camel case and snake case. Camel case is when the words are joined together, with the first word being lowercase and the rest being capitalized, as you see here. Snake case is when all the words in a variable name are separated by underscores, as you see in the second example here. So which one should you use? I personally recommend snake case. It's more popular within the Python community, it's arguably easier to read and type, and it's also popular in other programming languages. As such, for the sake of consistency, we'll be using snake case throughout this course. Now, using snake case is all fine and good, but keep in mind that the case you use is not as important as the actual name of the variable. It's always a good idea to give your variables meaningful, memorable names that describe what they're used for. For example, if you have a variable that stores a person's age, you could call it something generic like var or var1. But when you're reading through your code down the road, you'll probably have no earthly idea what the data stored in that variable actually means, which will make it much harder to quickly pick up where you left off and understand what your code is doing. Far superior alternatives here could be age or person age. Both of these options are clear and descriptive. Another important thing to consider is making sure your variable names don't overlap with Python keywords. So in Python, a keyword is a word that already has a special meaning in the language. Some common examples of Python keywords are for, while, in, if, and else, as well as the names of the two Python functions we've used, print and type, along with the names of lots of other Python functions we haven't explored yet. So if you use a keyword as a variable name, Python might think you're trying to use the keyword's special meaning instead of actually just using it as a variable. To avoid this confusion, it's best to just avoid using keywords as variable names altogether. Now, fortunately for your sanity, this doesn't require you to actually memorize all the Python keywords. That's because just about all programming environments where you might type Python code, including Colab, have a feature called syntax highlighting, which formats keywords in a given programming language differently than other words. Now, switching over to Colab, as an example, look at how the words Travis and for appear differently when I type them into a Colab cell. That's obviously because the word Travis has no special meaning in the Python language, while for does. The bottom line here is, as long as your variable name isn't formatted the same as a known Python keyword, like for, as you see here, you should be good to go. So to sum up, here are some best practices to keep in mind when you're choosing names for variables in Python. Follow one of the standard cases, like snake or camel. I recommend snake, as I mentioned previously. Use meaningful, memorable names to make your code easier to understand. Avoid using reserved words as variable names. And lastly, don't spend too much time deciding on the perfect name. It's not quite as important as, say, choosing a name for your kid. Save yourself time, avoid paralysis by analysis, and use these simple guidelines to quickly choose a name so you can get back to the fun and interesting parts of programming. Or maybe I should have just said interesting instead of fun and interesting. Because in the next video, we're going to explore an inevitable part of life for anybody who writes code that may be interesting, but definitely isn't most people's idea of fun. Programming errors. I'll see you there. So if you've done any programming at all, or even messed around with formulas and functions in a spreadsheet program like Microsoft Excel, chances are you've run into some errors. It happens to the best of us. And while these errors can occasionally be confusing, understanding the different types of errors you'll encounter and having a strategy for dealing with them can save you a lot of frustration down the road and ultimately help you become a better coder. Now, the first type of error we're going to talk about is syntax errors. Now, syntax errors are mistakes in the structure of your code that prevent the computer from even being able to interpret it. These errors can be something as simple as just misspelling a keyword, like the name of a function, for example. So here in the first cell of our Colab notebook, let's say I try to use the type function to return the type of the number 42.11. So I'll say type 42.11. 2.11. Now, even before running this code, the squiggly line before the word type is a hint that something is probably about to go horribly wrong. And this underlines, literally and figuratively, the point that when you're working in a code-aware editor like Colab that understands the language you're typing, you'll often know something is wrong before your code is executed. But nonetheless, I'm here to see this error through, daggone it, so I'll go ahead and hit that play button. And now we can see that since I'm clearly misspelling the type function, Python has no earthly clue what I'm talking about and throws an error. Remember, computers tend to be very literal-minded creatures and are very poor mind readers. Now, these error messages can look a bit intimidating at times, but they usually have helpful information nonetheless. The key is to read through them calmly and critically, looking for any keywords that may offer clues as to what went wrong. In this case, for instance, we see that Python is throwing a name error, and that the name TIPE is undefined. In other words, Python is telling us, in its awkward computery way, that it doesn't recognize the name of the thing that I entered. And of course, that's the issue. I got the name of the function wrong. So if I just change that function name to TYPE, and then run our code again, now everything works great. Now, as another example of a syntax error, let's see what happens if I try to multiply 2 by 21, but conveniently forget how to do multiplication in Python. So in a new code cell, innocently enough, I'll just type 2x21. I mean, that is, after all, how we learned to do multiplication in grade school, right? So now if I hit play, once again I get an error, and this time Python is nice enough to literally point an arrow directly at the culprit. In this case, X really does mark the spot, that being the X that I was silly enough to think would work for multiplication here. Now keep in mind, resolving errors won't always be quite this easy. But if you carefully read through the error and still can't figure out what went wrong, don't hesitate to look for help online by Googling or Binging or even ChatGPTing the error message. Colab even provides you with a shortcut to do this sort of thing that takes you directly to discussions on the programmer forum Stack Overflow specific to the error that occurred. But we don't really need Stack Overflow's help with this one, so let's go ahead and fix that ugly error. And now we're good to go. Now another, somewhat more subtle and insidious type of error is semantic errors. These are mistakes in the logic of your code that cause it to produce the wrong output, even though the syntax is technically correct. In other words, the computer is able to interpret your code, but it doesn't do what you intended it to do. So let's say I want to multiply 2 times 3, and then take the result of that to the second power. So first, let's take a shot at crunching that out in a new code cell. So I'll add that, and then I'll say 2 times 3 to the second power. Okay, so far so good. There are no squiggly lines anywhere, so I must be on the right track, right? And if I run the cell, no errors. And we get a sensible seeming result of 18. Or is it? Remember, our goal was to multiply 2 by 3 and then take the result of that to the second power. But 2 times 3 is 6, and 6 squared is 36. So while our code was technically correct from a syntax perspective, it wasn't actually doing what we intended. That's of course because I didn't use parentheses to override Python's default order of operations, which stipulate that exponentiation should occur before multiplication. So if I fix that by putting parentheses around our 2 times 3 expression, and then run our code one more time, now we get the intended result. Now, of course, the problem with an error like this is that if we aren't specifically looking for it, it can slip right past us. Semantic errors are sneaky. So how best to avoid them? Well, unfortunately, there's no ironclad way to prevent these kinds of errors altogether. But carefully reading through your code an extra time, while keeping in mind exactly what you want it to do, never hurts. I also recommend testing the output of your code versus what you expect, as well as thoroughly testing edge cases in more complex programs. Alright, so now that we've explored the kinds of things that can go wrong with Python code in general, up next we're going to look at something that can make our code easier for others and our future selves to understand. Comments. I'll see you then. So we've already seen how choosing meaningful, descriptive variable names can make our code easier to interpret and understand. But there's another feature in Python, or most any programming language really, that can provide meaning and context to every part of your code. Comments. So first off, what is a comment? Basically, it's a piece of text within your code that Python will ignore when it runs your program. Comments are typically used as a kind of explanatory note to other programmers or your future self. That may not seem like all that big a deal, but strung together, these notes can serve as a kind of reference manual for your code. If you're working on a project and it's been a few weeks since you last looked at your code, a series of clearly written comments can help remind you what's going on and what certain lines of code are doing. Alternatively, if you're working with a team of programmers or analysts on something, comments can help those other folks understand your code more easily. Now, let's get down to the actual syntax for comments. So let's say I have a line of code that prints the word hey in all caps, naturally, 37 times. Nice. Now, if one of my teammates was to come across this code, they might naturally wonder what the heck the purpose of this code is. And that's exactly where comments come in. So to create a comment, you simply type a £, and everything after the £, on the line where you typed it, will be ignored by Python when you run your code. So if I want to leave a little note here above this line of code, I can just type a £, at the beginning of that line and my note after that. So I'll enter down to add a new line above my current line of code, and then I'll type that £, and then I'll just type my note explaining that the purpose of this code is to annoy the reader as much as possible. And now when we run the cell, you can see that nothing changes about the output. Our original code still runs, but our comment has not affected the output whatsoever. And this isn't just the case if our comment consists of some random words. Even if I place a £, before actual working code, say our loud, annoying hey hey code here, and then run that, now nothing happens. And that's because we've commented out our one working line of code. This technique is sometimes useful when we have a line of code that we don't want to run just now, but would like to hang on to for future reference. For example, I could add a variation of our hey hey code here directly beneath our comments that prints hi, once again in all caps naturally, an astoundingly annoying 42 times. So I'll do that. Now I can keep the other line of code just in case, but don't have to worry about it running, unless I uncomment it by removing the £, of course. So if I wanted to do that, I would just remove the £, from my previous line of code, and then so we're not annoying our readers too much, I'll comment out my newest line of code, and then if I run that, now we get our original output. This technique is often used for testing new pieces of code. Using comments, you can comment out your original code and try out a new version, while retaining the option to revert back to the old code if need be. Now, it's worth noting that comments don't necessarily have to take up an entire line. Remember, anything after the pound sign will be ignored, but anything before it will still be run like any other Python code. For example, I can take our explanatory whole line comment and place it at the end of our working line of code here. So I'll just cut that line and then place it at the end of hey times 37. And now if I run the cell again, we get the same output. As you can see, the comment is still ignored and we still get the benefit of the explanatory verbiage. So when should you use what kind of comment? My recommendation would be, if the comment pertains to a single line of code, place it at the end of that line of code. If, on the other hand, the comment pertains to the program as a whole, or even a section of code, as opposed to a single line, I'd recommend using one or more whole line comments. Okay, so that's pretty much the basics of comments in Python. In the next video, we'll cover a more sophisticated alternative to comments available to us in Jupyter Notebooks like Colab, Markdown. I'll see you then. So if you're new to Jupyter Notebooks like Colab, you might have only used them to write and run code, which admittedly is all we've done thus far. And to be sure, the cells we've been working with in Colab are designed for just that. I mean, they're actually called code cells. But there's actually another type of cell that you can use in your Colab notebooks that gives you the ability to add, in effect, a supercharged version of comments, like the ones we saw in the last video, to your notebooks. And that is a text cell. So text cells are where you can write a kind of narrative about your code and data. They can include formatted text, hyperlinks, and even images, among other things. Now, text cells are highly useful for a whole host of reasons. For one, text cells are crucial for explaining the steps of your analysis or experimentation with your data, the reasoning behind your code, the sources of your data, and any conclusions or insights you may draw. They allow you to clarify the what, why, and how of your code. Now, aside from that, you can also use text cells to structure your notebook into meaningful sections, making your notebook easier to read and navigate. Now, as a feature I personally relate to, if you're teaching a coding concept, you can use text cells to provide a narrative or a step-by-step guide. And by the same token, if you're learning from a Colab notebook, the explanations in the text cells can help you understand the code. Text cells can also play a critical role for collaboration and reproducibility of your results. In other words, they help others understand your work and thus be able to reproduce it. This is really important when sharing your notebooks with colleagues, submitting them for peer review if you work in academia, or publishing them. Now finally, and most broadly, text cells can help you weave a story around your data, sharing insights and conclusions in the context of a broader narrative. This is useful in any situation where you want to communicate your findings to a non-technical audience, which as a data analyst, I can assure you is going to be a pretty big part of your professional life. So in summary, while code cells contain the technical meat of your work, so to speak, text cells are where you provide the contextual gravy that makes your work understandable, usable, and meaningful to others. So now that we know what text cells are and why they're useful, let's move on to an example that shows how they work in action. In particular, we're going to use text cells to explain the purpose and meaning of the examples in that Colab notebook where we explored different types of Python errors. So as a first step, I'll go ahead and create a copy of this errors notebook, which I can do by hitting File, and then save a copy in Drive. And then I'll just rename this to text cells. So now, for the first example inside our new Colab notebook, let's add a text cell whose content serves as a top-level heading for the entire notebook. So headings basically add value to your content by organizing it, making it easier for readers, including your future self, to navigate and understand your work. They provide structure to your notebook, essentially acting as signposts that guide the reader through different sections, topics, or stages of your analysis or narrative. So now let's go ahead and add that text cell, which we can do by simply hitting this plus text button up in the menu. And since I want this text cell to appear first in our notebook, I'll hit this up arrow here to move the cell up. And now to start adding text, I'll heed this prompt here and simply double click inside the text cell. And then for our heading text, I'll just type common programming errors. Now note that on the right side of this text cell, there's a preview window that shows exactly what we've already typed. But why? More on that in a second. For now, let's just click out of this cell to lock in our changes. And there's our header. Nothing too revolutionary here, at least so far. And it's true that simply documenting and explaining our code with just plain old unformatted text is plenty valuable. But Colab, and Jupyter Notebooks in general, give us the option to apply special kinds of formatting to this text. This formatting can make the meaning of the verbiage in our text cells clearer, which is, after all, kind of the whole point, right? So applied to our current example here, a heading for the entire notebook, we would ideally want to apply some kind of heading-specific format to this text. But how? Well, it turns out that Colab makes it just about as easy as applying formatting in a Word document. But because Colab is an environment meant for programmers, there is, of course, a bit of a techie twist, as you'll see in a moment. So to apply a heading-specific format to our new text cell, I'll first double-click the cell to activate it, then highlight the text, and now I'll hit this little button in the menu specific to the text cell that consists of two little T's. And when I hover over that, we see a tooltip that says Toggle Heading. So if I click that, note that a pound sign now appears before the text on the left side, and the text on the right side got noticeably bigger. Now, of course, the text getting bigger in the preview window makes sense, since we're trying to turn this plain old text into a heading, but what the heck is going on with that pound sign? Well, it turns out that when you apply formats using the graphical tools in Colab, behind the scenes, Colab defines those formats using a special language called Markdown. So Markdown is what's known as a markup language, similar to HTML if you've ever played around with web development. Markdown's purpose is marking up text by adding meaning to it with special symbols. And here, for a heading, that symbol is just a pound sign, followed by a space, followed by the text. Now you may be wondering, if this pound sign is all that defines a heading, can you create a heading by just typing this out? Absolutely. So to see an example, let's create a secondary heading pertaining to the first couple of examples in our notebook. A secondary heading is considered somewhat lower level and more specific than a primary heading, so it's appropriate for a heading that pertains to a section of a notebook as opposed to the notebook as a whole. So let's click out of our first text cell to lock in those changes, and then create another text cell, and again, move that up. And inside of this text cell, we'll simply type syntax errors to denote the section of our notebook pertaining to those. Now to apply level 2 heading formatting, we could simply highlight this text and then hit our little toggle button here twice. This would just place two pound signs before the text, which is Markdown's way of defining a secondary heading. But instead, we can simply type those out ourselves. So before our text here, I'll just type 2 pound signs and then a space. And right away over in our preview window on the right side of the text cell, we see that our heading text has increased in size accordingly, but is still somewhat smaller than the text in the main heading, as we would expect. Now at this point, you may have figured out that if you're a skilled typist and have a pretty good memory for picking things up quickly, you can use the buttons in the text cell menu to teach you the basics of Markdown, at which point your fast fingers can be off to the races, defining formats faster than any point-and-click operation could. And if that is you, go for it. Now, I myself may be the worst typist to ever do a job that involves typing all day, so I prefer to stick to the menus as much as possible. Oh well. So now that we understand the nuts and bolts of formatting, marking up text with Markdown, let's look at some other styles we can apply that add meaning to the notes and explanations in our text cells. So for our next example, let's take a look at organizing text into bulleted lists. So bulleted lists are used to present information clearly and succinctly, allowing for easy reading and comprehension of multiple related points or steps. So I'll create a new text cell, and I actually want this one to go between our two existing text cells. So I'll click our first one and then hit our plus text button. And there's our new text cell. And this once again reiterates that when you want to add a new cell to a Jupyter Notebook in a given position, just select the cell immediately before where you want your new cell to be positioned. Then click either your plus code button or your plus text button to create that cell. Now our bulleted list in our new cell is just going to list the two main types of programming errors, syntax errors and semantic errors. Now we certainly could start by typing the text out and then applying the bulleted list format later, but that's not the only way, or even necessarily the most convenient way to do it. So if you simply hit the menu button in the text cell menu for a given type of format, and for the bulleted list format, it will quite predictably be the button that looks kind of like a bulleted list, Colab will generate a kind of template in Markdown that will allow you to just fill in the blanks, so to speak. Note here that we're seeing another type of special syntax, this time an asterisk before the text instead of a pound sign. So for our content, for our first bullet, we'll just type syntax errors. And then for our second bullet, we'll type semantic errors. And then above these guys, I'll add a level 3 heading that just says there are two main types of programming errors. So that'll be 3 pound signs, a space, and then my text. And now clicking away, there's our bulleted list. So moving right along, now let's take a look at a similar example, but this time involving an ordered or numbered list. So ordered lists, in slight contrast to bulleted lists, are primarily used to present sequential steps, or perhaps prioritized points, or really any information where the order of the items is important for comprehension. So for our example here, let's go down to our last code cell in this notebook that demonstrates a semantic error, and then create a text cell after that in which we provide the reader with steps for preventing semantic errors. So once again, I'll just hit a button in the text cell menu to provide us with a kind of template, that being this little 1, 2, 3 button here. And here we see the Markdown syntax for an ordered list, which is, as is typical for Markdown syntax, pretty darn intuitive. And now for our first item, I'll just type, read through your code carefully. And for our second, I'll write test your code's output versus expected output. And now for our third item, I'm actually going to have to add some markdown syntax myself. But because we already see what that syntax looks like from the first two examples, I know that I can just go down here and type a 3, a period, 3 spaces, and then type my third item. So now I'll type test for edge cases. And finally, I'll click above our little ordered list and add a third level heading that just says steps to prevent semantic errors. And now clicking out of our cell, there's our nice, neat ordered list. Okay, so now that we've tackled organizing our text into lists, both ordered and bulleted, let's see how to strategically change the appearance of our text to give it an extra layer of meaning. We'll start by making text bold. So bolding text serves to emphasize key points or terms, which aids in readability and draws in the reader's attention to crucial information. So for our example, rolling back up our notebook, let's add a note directly after our very first code cell here that supplies the correct function name, TYPE, in bold. So let's copy this code here and then add a new text cell. And down below I'll type correct syntax and then paste in that code. And now I'll just highlight that misspelled function name and hit this B button on our text cell menu to format that text as bold. And again, of course, you can see that special markdown syntax that in the case of bolded text surrounds that text with 2 asterisks on either side. Now for a somewhat different kind of emphasis, you can use italicized text instead of bold text. Italicizing text is used for emphasis, typically to highlight key phrases or terms, which once again helps guide the reader's attention and interpretation of the content. So for our italics example, let's add a note before both of our syntax errors saying the type of error that will be generated by that code. Then we'll italicize the name of the error. So before our first syntax error, I'll add another text cell, and I'll just say this will generate a name error. And then I'll just highlight name and hit our I button here in the text cell menu. And then clicking away, there's our italicized text. Now I'll create another text cell directly above our misspelled function example and type, this will generate an invalid syntax error. And once again, highlight that text we want to italicize, click away, and there are those italics. Now before we move on, there's one particularly egregious error, not a Python error, my own personal error, that I just have to fix. In the text cell where I tried to specify the correct spelling of the type function, I somehow just kept the former tragically incorrect misspelling. So let me go ahead and fix that. Much better. Now we've already looked at quite a few options for formatting and organizing the content in our text cells, but there's plenty of other options right here in the text cell menu available to us as well. For example, we can insert emojis, or images, or even hyperlinks using this little paperclip looking button here. And if you want to do even more with your text cells than the options in this menu allow, you can always learn more about the markdown language I mentioned earlier that's responsible for all this formatting behind the scenes. A great place to start is the online reference to the markdown language, which I'll actually create a link to right here in a new cell. So rolling to the bottom of our notebook, I'll add a new text cell, and then a level 3 heading that just says Markdown Syntax Reference. And then below that, we'll hit this paperclip button to generate a template for adding a hyperlink to our text cell. And this little syntax template makes it pretty clear what goes where. We need to add the actual hyperlink in between these parentheses, so I'll go ahead and paste that in. And then we'll simply type the text that we want the user to see on the hyperlink in between these two brackets. So here I'll just type click here. And now if I click away, there's our link. And if I click that link, we're taken right to the official reference for basic Markdown syntax. Pretty cool. So there you have it. Now you have everything you need to create your own beautifully formatted, supercharged comments in Colab. Okay. So in this one, we're going to review some quirks of Colab that are important for you to understand before we start diving into more serious and fun applications of Python in the next section. So as an example to illustrate some of these quirks, here in a new Colab notebook, I'm going to create a simple investment calculator. So in our first code cell, we'll declare variables to hold our initial investment, the number of years over which the money will be invested, and the expected rate of return. So I'll call my first variable initial investment and set that equal to 20,000. Then I'll call my next variable num years and set that equal to 10. And finally, I'll call my third variable rate of return and set that equal to 0.1 or 10%. And now in a second code cell, we'll use the values in those variables to calculate the future value of our investment. So I'll declare a variable called future value and set that equal to a formula that will calculate the future value of our investment based on the values in the three variables in the previous code cell. Now don't worry if the math of this formula doesn't make a ton of sense to you. This is not a finance course, and the point we're illustrating here has nothing to do with the mechanics of calculating future value. But with that said, our formula is going to be our initial investment value. And note that if I just start typing the name of our variable, Colab is smart enough to recommend a list of options that start with those same letters, with our initial investment variable at the head of the list. So instead of typing out that whole name, and if you've taken my courses before, you know that there's nothing I hate more than typing, I can just hit my tab key to lock in that name. Typing 3 characters is certainly better than typing 18, I'd say. So now we'll multiply initial investment by, and here I'm going to have an expression inside a pair of parentheses, 1 plus our rate of return, and then I'll raise the expression inside of those parentheses to the power in our num years variable. Now, in a third code cell in our Colab notebook, I'll actually print out the projected future value of the investment that we're capturing in that future value variable. So here I'll just have an expression that starts with the text string, the future value of your investment is, and then I'll concatenate that future value in our variable with the plus operator. But of course, since that future value is going to be a number, I'll need to convert it to a string with the string function. So that's pretty much it for the code for our little investment calculator. Now note here that we could have, technically, put all of this code in a single cell. But it often makes code more readable, which is a major selling point of Jupyter notebooks like Colab, to break related chunks of code off into their own cells. So speaking of that, let's go ahead and run these cells, which I'll just do individually. So I'll run our first one, and then our second one, and then our third one. And it looks like the future value of our investment is about $52,000. So far, so good. Our code appears to work fine. But there are some pitfalls to keep in mind as you're working with Python expressions across multiple Colab cells in the way that we did here. For example, let's say I change one of my variable values and then run the first cell. So perhaps I change the value in my num years variable from 10 to 20, and then rerun that first cell. And now if I run the third cell, but I skip that second one, the value of our investment doesn't change, even though our money is going to be invested over a time frame twice as long as it was initially. So what the heck is going on here? Well, we're seeing this strange result because our third cell is getting the future value amount from the second cell, and the second cell hasn't been recalculated to account for the updates we made to the variables in the first cell. But now if we run the second cell and then run the third cell once again, there's our updated future value. Okay, now that we understand the importance of running cells in sequence, it seems kind of inconvenient to have to run each cell individually. So can we run them all at once instead? We sure can. So to see how that works, I'll once again tweak one of our variable values. Maybe I'll change our initial investment to $50,000. And now to get an updated future value without having to run all of these cells individually, I'll just hit Runtime in our Colab menu and then choose Run All. Nice. Not only are we learning how to save time with Colab's features, we're also apparently getting richer by the second. Now keep in mind that you don't necessarily have to run all cells at once to benefit from this kind of convenience. Let's say we don't want to change our variable values here in any way, but we would like to update our formula in the second cell that calculates the future value of our investment. In particular, perhaps our goal would be to calculate interest monthly, not annually, which we can accomplish by dividing the rate of return piece by 12, then multiplying the number of years by 12. So here in our formula, I'll divide rate of return by 12, and then instead of taking that to the power of num years, I'll take it to the power of num years times 12. Now once again, if that formula seems a little weird, don't worry about it too much. We're not trying to learn the gory details of high finance here. So surveying our updated notebook, we can see that our inputs in the first cell haven't changed, but the formula in the second cell has. In other words, we don't need to run all the cells. We just need to run everything from the second cell and below. And fortunately, there's a built-in command for this as well. So with our second cell selected, I'll go back to my Runtime menu and then choose Run After. And as you can see, we got a slight lift in the future value of our investment by calculating our interest monthly rather than annually. Now, just the ability to automatically run cells in sequence doesn't necessarily solve every problem either. That's because, regardless of whether you're running the cells or if Colab is running them all in sequence for you, they need to be run in a logical order from top to bottom. And that's because Colab, and Python programs in general, execute code from top to bottom. To show you what I mean, let's move the cell with our variable declarations to the bottom of our notebook, which we can do using this down arrow icon in the cells menu. So I'll just click that once, and then once more. So now, just to establish a baseline, take note of the future value that our little program is currently returning here in our second cell. And now, let's see what happens if we change one of our inputs down here in the third cell. Say the rate of return to a very generous value of 25%. Now, you don't have to know a lot about investments to know that our future value should go up substantially by increasing our rate of return that much. But now let's see what happens if we choose runtime and run all. Our future value in our second cell doesn't change. And that's because the code that crunches out the future value calculation runs before Colab gets to our updated variable declarations. So it's basically still using the old values in the variables. But now if we rerun all the cells again, this time our result does take the new variable values into account, since that last cell had a chance to run the last go around. You see, Colab and Jupyter Notebooks in general remember variable values, so to speak, within your current session or runtime. More on that in a moment. But still, I think you can see why this could potentially lead to misinterpreting the results in your notebooks. So the takeaway here is to just keep your code cells arranged in a logical order within your notebook. Now, in other circumstances, this illogical ordering of cells can actually cause your code to error out, as opposed to simply producing confusing results. Let's say you close your notebook and then reopen it later on. This causes the notebook's runtime, which is basically the engine that runs your code behind the scenes, to reset, meaning the state of your code is reset to a blank slate. The main effect of this is that any values stored in variables, values that the runtime remembered, are lost, and we'll need to rerun the code to get them back. Now, it turns out we don't have to close out of Colab to see how this works. We can actually just restart the runtime directly from the menu, which will have the same effect as closing the notebook and reopening. So let's do that. So I'll choose runtime and then restart runtime. And now Colab dutifully warns us about losing our program's state and variable values, but we already know what we're getting ourselves into, so we'll hit yes. And now if we try to run all cells again, as predicted, our code errors out, since the code in our first cell is referencing variables that haven't even been declared yet. So now let's go ahead and move that last cell back up into the first slot where it belongs, and then rerun all cells. And now everything runs without complaint. Nice. Okay, so there's one last pitfall of working in Colab/Jupyter Notebooks I want to acquaint you with, and that's how to handle long-running code. Now, the little programs we've been working with so far execute almost instantaneously, but as you progress to more advanced applications of Python, you'll occasionally run into situations in which your code just keeps running and won't stop. Sometimes this means you're executing an operation that's just too big for your computer, or the free tier Colab runtime in this case, to handle, and other times it may mean there's something wrong with your code. In either case, you'll definitely want to have the option of stopping your code from executing. To see an example of this, I'm going to code something called an infinite loop. Now, you don't need to understand exactly what's going on here just yet, or even remember how to do this. In fact, I think I want you to forget how to do it because infinite loops are to computers as aluminum foil is to microwaves. They do not play well together. So proceeding with caution, in another cell here, I'll code up that infinite loop. So I'll say while 1 equals 1. And intuitively, we would expect 1 to continue to equal 1 for quite a long time, right? And then while that's true, we'll simply print, hey. So now when I run this cell, you see that the code keeps running and running and running, and will keep running forever actually until the folks at Google boot me out of Colab for good, or until I stop the code from running myself. I like that option better, so to do that, I'll just hit the interrupt execute button right where the run cell button was. And just like that, the code pauses, and I don't have to create another account just to keep using Colab. Although, looking at the sheer number of times I printed the word hey, Google might just come after me anyway. So on that note, I think I'll step away from Colab for just a bit, and I'll hopefully see you in the next one. So in this one, we're going to cover some of the truly foundational concepts in Python: objects, properties, and methods. Now, fair warning, this stuff is a bit abstract, in the clouds if you will, and I'll only spend as much time on it as absolutely necessary before we get to the practical applications that are why I'm talking about this stuff in the first place. Now, with that said, objects are the fundamental way of organizing data and functionality in Python programs, and indeed in many other languages. In fact, languages such as these are known as object-oriented languages. Python is so object-oriented, in fact, that just about everything in Python is an object. A numeric value like the number 5, an object. A text string value like your name, also an object. A variable that stores a value like those two we just mentioned, object. What else? And even a function like the print or type functions we've worked with, you guessed it, objects. Now you may think of these objects as pretty simple phenomena, and compared to some of the other objects we'll encounter in Python later on, they are. But even simple objects like text strings have a little more going on under the hood that you might expect. You see, objects can have any number of attributes and methods. So what the heck are these? Well, let's take that under the hood metaphor just a little bit further. You can think of objects in computer programs as a way to model or represent the way actual physical objects work in the real world. Consider a car. It has properties or attributes like its height, its length, its weight, its color, and so on. But it also has functionality or behaviors, things it can do. Say accelerate, brake, beep the horn, turn on its headlights, and so on. A different sort of object, like a boat for example, would have its own distinct set of attributes and behaviors. Likewise, objects in Python, right on down to something as simple as a plain old number, can have attributes and behaviors as well. Except those behaviors, in Python and many other programming languages as well, are called methods. Now we've actually already seen an example of an object attribute earlier on when we used the type function to return the data types of various values, which could of course be considered attributes of those values. But we haven't seen how to take advantage of the methods an object has to offer. So let's quickly jump into Colab and see how that works. So as an example, in a new code cell in this Colab notebook, I'll declare a variable called obj, short for object, and then I'll set that equal to the text string, "Can you hear me now?" And then I'll simply reference that variable on the next line of the cell. Now nothing terribly special seems to be happening here so far, but look at what happens if I follow this value with a simple dot. Now, Colab, via that same autocomplete feature that suggested variable names for us in the last video, gives us a list of behaviors, or methods, that come built right into this text string object. Now keep in mind that the methods, or properties, available to an object vary, depending on what kind of object it is. Just like a boat and a car would have different properties and behaviors. So now let's scroll down this surprisingly long list of methods until we find one called upper. So now I'll click that one to select it. And just like that, the method name appears after the dot. But we're not quite done yet. You see, using or invoking a method is pretty much the same thing as using a function like print or type. The only difference being this function is specific to our particular object here. And just like with functions, we need to follow the names of our methods with parentheses and include any arguments the method might require inside of those. Now, the upper method doesn't require any arguments, so we'll just add those parentheses and then run our cell. And just like that, you can probably infer what the upper method does. By uppercasing all those letters in our text string, our innocent little message has now been transformed into something incredibly loud and obnoxious. Cool. I mean, I guess. So the main takeaway here is this. Everything in Python is an object. Objects, even simple ones like text strings, have attributes and methods. And we can access those properties and methods via something called dot notation, which simply means following the name of the object with a dot, then the name of the given attribute or method. And here we see a general example of what dot notation looks like in code. Pretty simple, really. It's just the name of the object, followed by a dot, followed by either the property of the object you want to reference or the method you want to invoke. Now, switching gears a bit, from syntax back to a conceptual view of objects. The numbers and text strings we've worked with so far are kind of like the single-celled organisms of the Python universe. They're about as simple as it gets. But objects can get a lot more complex than that. Blue whales or elephants instead of amoebas, if you will. But that doesn't necessarily mean those more complex objects are harder to work with. It just means they have more attributes and methods to work with and more ways to work with them. You see, objects are meant to abstract away complexity, meaning we don't need to understand the inner workings of those objects to use them effectively. Just like you don't need to understand exactly how brakes work in a car to use those brakes, thank goodness, you also don't necessarily need to understand how functions and methods in Python work to use those either. In fact, it would be impossible to work with a program if we had to understand every single building block that every piece of code was built on all the way down. Okay, so to that, now I'm really going to blow your mind. Not only do objects have attributes, but those attributes can actually be other objects with their own attributes and methods. And those attributes can be other objects, and so on and so on. It really is objects all the way down. As crazy as that may sound, it's really the best way to organize the massive complexity baked into a fully featured programming language like Python. Going back to our car example, sure, a car has attributes like height, weight, and color. But what about, say, its engine? Isn't that also an attribute? And if the engine is an object that is also an attribute of the car, wouldn't, for example, one of the pistons in the engine, assuming you don't have an electric car, of course, be an attribute of that, with its own distinct set of attributes and behaviors? And obviously, you could keep going in this manner for a long, long time. But I think you get the point. And if you do, we don't really need to torture ourselves with all of these slides, analogies, and abstractions anymore. Because just this understanding is all we need to start using all the goodies Python has for working with data. I mean, that's why we're here, right? We'll get our first taste of that in the next video. See you then. So now that we have a general understanding of how Python's features are organized and how to access those features via dot notation, it's time to dig into a practical example. So accessing the methods of a simple text string is one thing, but you're probably wondering, where does the actually, cool stuff live? Well, much of it can be found in what are called modules. So you know how you can have a toolbox of different tools that you can use for different kinds of projects? Think of modules in Python as being similar to that, but for programming. Instead of a hammer and a screwdriver, you have different chunks of code, typically oriented to some general category of functionality that you can use to make your programming life a lot easier. Now remember how complex objects in Python can contain other objects, like a car contains an engine, which in turn contains all sorts of other parts? Well, likewise, collections of modules, in turn, can be contained within something called a library. So if modules are toolboxes, libraries are the garages, so to speak, that all those toolboxes are contained in. And fortunately for us, Python keeps those garages a lot better organized than most people's garages I've seen, including my own. So one great example of a Python library, and the one we'll be spending much of the rest of the course working with, in fact, is Pandas. So Pandas is a library that makes it super easy to work with data in Python. Let's say you have a big text file or spreadsheet with a lot of information in it, and you want to analyze that data programmatically with Python. Using Pandas, you can read that spreadsheet into Python and then use all sorts of cool functions and methods to slice and dice the data however you want. You can filter it, group it, and even visualize it, all with just a few lines of code. In short, Pandas makes data manipulation about as simple and efficient as possible. Now, aside from Pandas, there are libraries for almost any functionality you might need, from connecting to web services, to creating graphical user interfaces, to running machine learning models. And if you can't find a library that does exactly what you need, you can always write your own code, or use a combination of functionality from different libraries and modules to create your own solution. But for now, just Pandas will give us plenty to chew on. Now, to use Pandas, as with any other library in Python, we'll have to import it first. This is kind of like telling Python that you want to use the toolboxes full of tools contained in that library for your project. Once you've imported a library, you can then use all the handy functionality it contains to make your own code more powerful and efficient. So the actual code to import the Pandas library into a notebook is as follows. We first use the import keyword, followed by the name of the library, which in this case is Pandas. Now you'll notice that Colab is suggesting that we type Pandas as PD, and we can take it up on that suggestion by hitting the Tab key. But of course that begs the question, what exactly does as PD do once we've already specified that we want to import Pandas? Well, that part of the syntax to import a library is optional, but it's a common convention to use it to alias the name of that library, so that every time we refer to it in our code, we can use the shorter PD instead of typing out Pandas every single time. So to reiterate, if we only set import Pandas, we'll still have access to all of Pandas functionality in our notebook, but every time we call that functionality, we're going to have to precede our code with pandas dot. But by aliasing that library as PD, using the as keyword, now we can prefix our code with simply PD. At the end of the day, it's really just about convenience and saving yourself a bunch of keystrokes over time. But much more importantly, once we've imported this library, we can start using it to do all sorts of cool things. We'll be exploring lots of these in the next few sections, but for starters, let's see how we can read data from a CSV, or comma-separated values file, using Pandas' built-in read CSV function. Not to make things too confusing, but when you're working specifically with modules, or libraries like Pandas, we use the word function instead of method as we saw with other types of objects in the last video. This distinction doesn't really matter all that much, but it's worth knowing so the terminology doesn't confuse you. But I digress. Back to the task at hand. Now, before we use read CSV to import a CSV file, we first, need some sort of CSV file to import. And we also need to put this file within reach of our Colab notebook. Now, there are a few ways to access data files from a Colab notebook, but the easiest is to just import the file directly into the notebook. This has the advantage of being very straightforward, but there's also a major drawback to this approach. And that's that the file you import doesn't persist past your current notebook session. Now, putting that into plain English, this means if you import a file using this method, then close your notebook and reopen it, your file will be gone. And then you'll have to import it all over again to use it. Now, this obviously isn't ideal, and we'll actually be learning another, more robust way of accessing files in Colab later on. But for now, this simple method should work just fine. So to make an example file available to us in Colab, I'll hit this folder icon in the menu over to the left of our Colab cells that displays a Files tooltip when we hover over it. And now clicking that, we reveal a submenu. And inside of that, if I click this button with an upward pointing arrow that says Upload to Session Storage, that opens a dialog box that allows me to navigate the file system on my computer to select a file to import to my Colab notebook. Now here, inside a folder on my computer, I have a CSV file called STEM Salaries, which you should be able to find as a downloadable resource in the course resources. So this file contains salary data for people working in so-called STEM jobs. That is, science, technology, engineering, and math. Pretty relevant info for someone learning how to analyze data with Python, I'd say. So now to import this file into our Colab notebook, I'll simply select it and then hit Open. And now, after waiting a few moments for that file to upload, we'll dismiss this warning that Colab gives us, informing us of what I already explained, that this file is going to disappear as soon as this session or runtime ends. In other words, whenever we close out of this Colab notebook. So we'll click OK to dismiss that. And now that the STEM Salaries file is safely inside of our Colab notebook, which we can see in this menu over on the left, which I can now close, by the way, we're ready to read that file into Python using the read CSV function from Pandas. So to do that, in a new code cell, I'll type out a variable to store our data set in, and I'll just call that data. Then we'll type out our abbreviation for the Pandas library, PD, and now we can invoke the read CSV function, which we access via dot notation just like we learned in the last video. So I'll say PD dot read CSV, and this function takes a single argument, that being the path of the file that we're importing to Python. Now, since we uploaded the file directly to our Colab notebook, specifying the file path, as it were, is easy. The file lives in the notebook, so to speak, so the path is just the name of the file. Okay, so since we're calling a function, we know we'll need parentheses after the function name, and then we'll pass in that argument, which will just be the name of our file, which was STEM Salaries.csv. And then I'll simply reference that data variable that's going to hold the output of the read CSV function on the last line of this cell, and then run it. And here I've run into an error, which I can't blame on Python or Pandas. I mean, who could blame something on Pandas? They're pretty darn cute, right? So this one is entirely my fault. I neglected to run the first cell in our notebook which actually imports the Pandas library to begin with. So now when I reference PD in the second cell, Colab has no earthly clue what I'm talking about. So let's run that first cell, and now our second one again. And just like that, there's a preview of our data. Pretty darn cool. Now just imagine how much code you'd have to write to wire up this kind of functionality from scratch. You'd have to tell Python explicitly how to navigate through a file system, how to open a file, how to iterate line by line through the rows of data, how to display that data to us in Colab, and so on. But thanks to the power of libraries, we don't have to worry about any of those gory details. We write a few lines of code, and it just works. And let me tell you, we are just getting started. Read CSV is the obvious place to begin our exploration of Pandas, but it's just one drop in the ocean of functionality Pandas has to offer. For that matter, we've barely scratched the surface on all the things just the read CSV function can do. But don't worry, we're going to start digging into all of that very soon. In the very next section of the course, to be exact. But before we get there, we're going to round out our understanding of the fundamentals of Python with a brief survey of data structures, which give us far more flexibility and power when working with complex data than the simple integer, float, and string data types we've played with thus far. That's coming up in the next one. I'll see you then. So now that we've covered the very basics of Python, over the next 3 videos, we'll be digging into some of Python's core data structures. I mean, this course is all about working with data, right? But what exactly is a data structure, you ask? In short, it's a specific way of organizing and storing data in a computer program so that it can be used efficiently. Data structures allow for operations such as accessing, inserting, deleting, finding, and sorting data in various ways. Now, among the data structures available in Python, perhaps the most pervasive are lists. Think of lists like containers where you can store different types of data. Numbers, strings, and confusingly enough, even other lists. Lists are very commonly employed in analytics and data science because in addition to being capable of storing a variety of data types, they're also great at handling and manipulating data, from storing multiple values of a data set to performing operations on those values. So with all of that said, let's dive right in and see how we can work with lists using Python. So here in a new Colab notebook that I've named Lists, my first order of business will simply be to create a new list. Now in Python, creating a list is as easy as putting different values between square brackets, separated by commas. So if I want to assign a list of values, say the numbers 1, 2, 3, 4, and 5, to a variable called myList, that would look like this. I'll just type myList equals, and then a pair of square brackets, and then inside those brackets, I'll simply type out the values separated by commas. So now entering down, and then simply typing the name of that variable, since we know that Colab by default will display the output of the last line of code in a given cell, and then I'll run that cell, and there's our list. Now, one of the more powerful features of Python lists is that they can contain multiple types of data. This includes strings, integers, floats, and even other lists. So let's see an example of that. So creating another code cell, I'll define another variable called mixed list, and I'll again assign a list to this variable, but this list is going to contain values of multiple different types. So first we'll have the number 1, an integer, and then the text string 2, and then the float value 3.0, and then for the fourth value, we'll actually have another list, a list within a list. And inside this list, I'll have the text string 4 and the integer 5. And then I'll simply reference my variable on the next line of code and run our cell. And there's our new list, which contains integers, floats, strings, and another list. Okay, so now you know how to create a list. Great. But how do you access the items inside the list? Well, that's where indexing comes into play. So in Python, the index of a list starts at 0. That means the first item in a list is at position 0, the second item is at position 1, and so on. Now, applying that to actually fetching items from lists, you can access an item in a list by simply referring to its position within that list inside of square brackets. For example, let's say I want to fetch the very first item from our myList list that we defined in the first cell of our notebook. So to do that, I'll add a new code cell, and then I'll say first item equals myList, and then immediately after the name of the list, I'll type a pair of square brackets, and then inside those brackets will be the index or position of the item I'm targeting within that list. Of course, understanding that the first item is at index 0. So since we're targeting that first item, I'll type 0 here, and then type first item below that, and then run our cell. And sure enough, we have successfully fetched the first item from that list. Now, since we know that lists can contain other lists, in fact, we just defined one that does, let's now take a look at how we can access items inside those nested lists. So it's actually quite simple. You just add another set of square brackets with the index of the item in the nested list. So let's say I want to access the first item in the nested list inside of our mixed list list. Phew, that's a lot of lists. Anyway, our first step would be to access the nested list itself. So let's say we want to fetch that value into a variable that we'll call nested item. Now our first step will be, as I said, to just fetch that nested list itself. And we can see from looking at mixed list that that nested list is at position 4 inside the list, which means it's at index 3. So we'll use index 3 inside of our brackets here. And then, of course, I actually need to type the name of the list that we're accessing the third index of before those brackets. And now let's see what we get back when we run that. We get a list containing the string 4 and the number 5. That is the same list that lived at index 3 in our mixed list list. So now to fetch the first value in that list, I just need to add another pair of brackets after these, and then the index of the value we're targeting inside of that nested list, which, since we're going for the first value, will be index 0. So now rerunning our cell, there's the first value in that nested list. Now up to this point, we've only created lists and then accessed items from them. But one of the most important features of a list is that you can modify it once you've created it. So for example, what if you made a mistake and just want to change an item in your list? Well, it turns out that's extremely easy to do. To change the value of a list at a given index, you use pretty much the same syntax that we've been using to fetch a value from the list at a given index. Same brackets, same zero-based index. So let's say, for example, we want to change the second value in our myList list from the integer 2 to the text string 2. To do that, I'll add a new code cell to our notebook, and then I'll just say myList, and then specify the index, which is 1 since we're targeting the second item, and then I'll set the value at that index equal to the text string 2. You can think of this kind of like the difference from retrieving the value in a variable and setting the value of a variable. The only difference between getting and setting in both cases is really just which thing is on what side of the equal sign. So now let's see if this code did what we thought. So I'll type out the name of our list and then run this cell. And just like we expected, the second value of that list has been changed from the number 2 to the text string 2. Now, speaking of modifications you can make to lists, you can also add an item to your list as opposed to simply changing one of the values that's already there using the append function. This function will add a new item to the very end of the list. Now, to make things interesting, let's add a list, a nested list that is, to our existing mixed list list. So once again, creating a new code cell, I'll say mixed list dot append. So as you can see, append is a method that's available on lists. And then we simply pass an argument to the append method that consists of whatever data we want to add or append to the end of the list. And in our case, that will be another list, which will contain the values 6.0 and the text string 7. And then, of course, we'll check to see what's inside of our mixed list as a result. So running that cell, there's the list we passed to the append method at the very end of all the other items inside of mixed list. Now, speaking of functions and methods that are applicable to lists, to find out how many items are in a list, you can use the len function. So for example, let's say I want to return the number of items in our mixed list here. So in a new code cell, I'll simply type len mixed list. Now running that, we get the number 5, which depending on your perspective may be intuitive or a little bit surprising. We do technically have 5 items in the list: the number 1, the text string 2, the float 3.0, and then 2 lists. But we also have 7 total data points because we have 2 lists inside of our main list. But the len function returns the number 5 in a case like this because it only cares about the number of items in the list and doesn't care if some of those items contain items themselves. All right, so don't worry if none of this has seemed all that practical just yet. Practical applications are coming up very shortly, just as soon as we start playing with pandas. Not the furry kind, of course. Remember, the whole purpose of this quick survey of Python is to give you just enough of a foundation in Python to use pandas effectively. In other words, I want us to get to the fun stuff as fast as possible. But we have just a small handful of other things to cover before we get there. So up next, we're going to take a look at another data structure in Python that's very similar to lists, but with one crucial difference. I'll see you then. So in this one, we're going to explore another handy data structure in Python, the tuple. So tuples are a bit like lists, but with a crucial difference. They are immutable. This means that once a tuple is created, you can't change its content. Now this might sound limiting, but it actually makes tuples the perfect choice when you need to store data that shouldn't be modified. So go grab a cup of coffee, or maybe some tea, or a Red Bull if you're not into the whole coffee thing, and let's dive right into tuples. So here in a new Colab notebook, my first task will be to create a brand new tuple. And just like with lists, creating a tuple is very simple. In fact, the only difference between creating lists and tuples is that instead of using square brackets to surround the values inside the tuple, we use parentheses. So if I want to create a tuple called my tuple, I'll simply throw a pair of parentheses after the equal sign, and then a series of values separated by commas. After the last video, this probably looks pretty darn familiar. And then if we reference that variable on the next line of code, and then run our cell, there's our new tuple. Now, just as with lists, which you've probably guessed by now will be a recurring theme in this video, tuples can contain multiple different types of data. This includes strings, integers, floats, lists, and you guessed it, even other tuples. So to see an example of this, I'll add another code cell and then create a variable called mixed tuple. And to this, I'll assign the number 1, the text string 2, the number 3.0, a list containing the text string 4 and the number 5, and then a tuple containing the text string 6 and the number 7. So now if we reference our mixed tuple variable on the last line in this cell and then run it, clearly Python was able to handle that somewhat complex data structure with no problem. Now, similar to the other operations we've performed thus far, accessing items from a tuple, again, works almost exactly like accessing items from a list. Like lists, tuples use zero-based indexing, in which the item at the first position in the list is considered to be at index 0. And like with lists, we access those items using a square bracket notation. So let's say I want to fetch the second item from our mixed tuple. So I'll create a new code cell, and then I'll simply say mixed tuple, and then a pair of square brackets, and then the number 1, because the item at index 1 will be the second item in the tuple. Now running this, there's the text string 2, which is in fact the second value in mixed tuple. Now, given that tuples can contain other tuples and lists, as we've already seen, the need will often arise to access items within those nested structures. And this turns out to be just as straightforward as fetching items in nested lists. You just need to add another set of square brackets with the index of the item in the nested tuple or list. So let's say I want to fetch the second item in our nested tuple inside of mixed tuple. So I'll create a new code cell, and then I'll say mixed tuple, and first I'll access that tuple itself, which is at index 4 because it's the 5th item in the tuple, and then running our cell to confirm that that is the case. There's our tuple. So now to get to the second item inside of that tuple, I just need to drop its index within that nested tuple inside of another pair of brackets. So that will be index 1. So now running the cell again, easy peasy. Just like that, we fetched a value nested 2 layers deep inside of a tuple. And keep in mind that this nesting can go on and on and on. We could have lists inside of tuples, inside of lists, inside of tuples, inside of other tuples. But as you can imagine, accessing items more than a few layers deep becomes quite the chore. So in general, nesting data points that deep inside of these layers of data structures is not exactly a great idea. Now moving right along, remember how I said that tuples are immutable? Well, to reiterate, that means that you can't change an existing tuple once we've defined it. And if you try to modify an item within a tuple, Python will give you an error. So just to prove that to you, let's try to change the value at the second position inside of my tuple to the text string 2. So I'll add a new code cell, and then I'll say, just like we would with a list, my tuple index 1 equals the text string 2. Now running this cell, we get a type error saying the tuple object does not support item assignment. Similarly, appending data points to the end of a tuple, like we did with lists, is also off the table. So if we add a new code cell and I try to add, say, the number 6 to the end of my tuple, so I'll say my tuple dot append 6, and then run that. Once again, an error. In this case, Python's telling us that the tuple object has no attribute append. So whereas append is built into any list as an attribute that allows us to tack values onto the end of that list, tuples have no such feature. Now, with that said, tuples do allow us to use the len function to return their length, just like we saw with lists. So let's say I want to get the length of our mixed tuple. All I have to do is type len mixed tuple, and then if I run our cell, there's the number of items in that tuple. Obviously not including the count of data points inside of those nested data structures, that being the list and tuple inside of the outer tuple. Okay, so that's pretty much the basics on tuples. Now, despite this whole immutability thing that we saw can result in errors if you try to modify tuples in any way, tuples are nonetheless quite versatile and useful in a variety of scenarios, especially when you want to ensure certain data doesn't change. Speaking of which, you might be wondering when you should use tuples and when you should use lists, since they seem quite similar. As a general rule, you'll want to use lists when you have a collection of items that might need to be changed as your program runs. And you should use tuples when you have a collection of items that should not be changed under any circumstances. For example, if you're writing a program to keep track of your daily to-do list, you'd probably want to use a list. I mean, hey, it's right there in the name, to-do list. That's because as you complete tasks and think of new ones, you'll need to add and remove items. Now, on the other hand, if you're writing a program that involves the days of the week, you could use a tuple for that because the days of the week should never change. But remember, as with so many things in programming, Python won't stop you from storing something that ideally should be in a list in a tuple, or vice versa. It's really up to you to decide which one is more appropriate based on what you need to do with the data. All right, so now that we have a grip on tuples and lists, up next, we're going to complete the trifecta of the big 3 data structures in Python when we explore dictionaries. I'll see you then. So this go around, we're going to explore a very powerful data structure in Python known as a dictionary. So Python dictionaries are kind of like, well, real-life dictionaries. In a real-life dictionary, you have words and their corresponding definitions. In a Python dictionary, instead of words and definitions, you have keys and values. Each key is unique, and the values can be just about anything. Numbers, strings, lists, tuples, and, you guessed it, even other dictionaries. Let's dive right in and see what this all looks like in code. So here in a new Colab notebook, my first task will be, just like we did with lists and tuples, to create a new dictionary from scratch. So creating a dictionary in Python is as simple as placing items inside of curly braces, separated by commas. Just like with lists and tuples, but with curly braces instead of brackets, as with lists, or parentheses, as with tuples. Now, other than that, the main difference between dictionaries and lists and tuples is how the items themselves, those things inside the curly braces, are structured. Instead of being raw data points, or even another data structure, like a list or a tuple, a dictionary item has a key and a corresponding value that together are expressed as a pair, with the key and value separated by a colon. To see what this looks like, let's create a simple dictionary where the keys are English words and the values are their French translations. So I'll create a variable called translations. And then to set up my dictionary, I'll type a pair of curly braces. And now to define the first item in my dictionary, I'll start with the key, which in this case will just be an English word, and I'll go with hello. So I'll just type the string hello, and then a colon, and now I'll specify the value that is to be associated with that key. And since we're making a dictionary that's mapping English words to French words, that will be the French word for hello, which I think is bonjour. I apologize to any French-speaking listeners out there who might be throwing things at their computer after hearing my disastrous attempt at French pronunciation. But nonetheless, I'll type bonjour. And of course, since these values are simply text strings, they have to go inside of quotes, just like any other text string. And so with this, we have actually just defined the first item of our dictionary. We have our key, hello, and our value associated with that key, bonjour. Now note that there's nothing really magical about either of these values in terms of what type of data they have to be. I chose to use strings for both the key and the value, but I could just as easily have used an integer, for example. So now that we have our first item, let's type a comma and then move on to our second. So in this case, we're going to translate the English word for yes into the French equivalent. So I'll say yes, and then a colon, and then oui. And then finally, I'll translate no to its French equivalent, which I believe is non, although that pronunciation does not feel nearly fancy enough to be French, and is almost certainly not accurate. My apologies to everyone. As someone from Kentucky, my closest encounters with French culture were probably French fries. But my struggles with pronunciation aside, let's go ahead and see if this is actually a valid dictionary. So I'll type out the name of our variable on the next line, and then run our cell. And sure enough, Python accepted what we typed as a dictionary. Now that of course begs the question of how to access values from within our dictionary. So just like with defining a dictionary, it works a little differently than with lists and tuples. Namely, we need to point to the value we're trying to fetch using its corresponding key. But we still make use of the same bracket notation that we used to fetch an item from a list or a tuple. So in a new code cell, I'll simply try to fetch the French word for hello. So I'll say translations, and then a pair of square brackets. And into these, instead of an index, I'll pass in the key that corresponds with that value. So that will be just the word hello. Now running the cell, there's our translation. And what's great about knowing how to fetch values from a dictionary is that it gets you 95% of the way to also knowing how to modify values in a dictionary. That's right, like lists and unlike tuples, dictionaries are mutable, which means that after you define them, you can change their values or even add values to them. So let's say hypothetically that for some reason, the powers that be who maintain the French language have decided that the French word for no, instead of being N-O-N, will be the slightly more enthusiastic N-O-O-O-N. So now, to update the translation in our little dictionary, in a new code cell, I'll say translations no equals N-O-O-O-N. And now if we reference that translations variable on the last line of the cell and then run it, we can see that that value for the key no has been updated accordingly. And changing existing values in a dictionary isn't the only way we can modify a dictionary after the fact. We can also add brand new key value pairs. For example, let's say we want to add a French translation for another English word, or phrase in this case. Say thank you. So in a new code cell, I'll say translations thank you equals merci. Note that the only difference here between adding a new key value pair to our dictionary and updating an existing key value pair is that the key we specify in this case doesn't already exist in the dictionary. If it does, we would simply be overriding the value associated with that key. But if that key does not exist in the dictionary, we'll add a whole new key value pair. So now let's reference translations on the next line and then run our cell. And as you can see, we have that brand new key value pair that translates thank you into French. Now lastly, just like with lists and tuples, you can also use the len function to return the number of items, that is to say the number of key value pairs in a dictionary. So in another code cell, if I say len translations and then run that, we get 4, which is the number of key value pairs in our dictionary. So at this point you might be wondering, why would you opt to use a dictionary when data structures like the lists and tuples we've seen so far also technically give us the ability to store multiple data types and nest other data structures any number of layers deep? Well, for one thing, dictionaries are optimized for fast data retrieval. Python can quickly access any value in a dictionary just by knowing its key, even in really large dictionaries. This can be much quicker than having to traverse a list or a tuple, potentially speeding up your programs. But much more important, at least I would argue, is that the key value structure of dictionaries makes it much more intuitive to work with complex data. To see what I mean, let's consider another example that perhaps better illustrates the benefits of using dictionaries. Suppose you want to store information about a group of students, including their name, age, and grades. Now here's how you might do this using a list. So in a new cell, I'll define a variable called students list, and then I'll define an outer list, and then inside that list, I'll create a nested list for our first student, and her name will be Alice Doe. Her age will be 20, and then I'll store her grades in yet another list nested inside of this nested list. And those will be 85, 90, and 95. And then a comma, and then I'll do something similar for maybe 2 more students. So I'll just copy and paste that list, and then change the details. So my next student will be Bob Smith, and he'll be 22, and his grades will be 88, 92, and 90. Then finally, we just have Todd, who's 21, and has grades 80, 85, and 78. Now, Alice and Bob are doing just fine, but Todd may want to consider taking one of my courses. Not to shamelessly self-promote. Now, the thing about working with nested lists like this is if we want to access a particular piece of information, we need to know the position of different things inside of each of these lists. So, for example, if I want to know Todd's grade on assignment 2, I need to know that the list for Todd is the third list in the overall students list, and then that the list that contains Todd's grades is the third list inside of his list, and then that the assignment I care about is the second item inside of that list. Now, while it's totally feasible to fetch this information, which we can see if I just run this cell and then add a new code cell and say students list, and then I'll access Todd's list at index 2, and then the list containing his grades also at index 2, and then finally the grade for the second assignment at index 1, and then run that cell. Sure enough, there's his grade on the second assignment. Now again, while this works, you can probably imagine how this process can become pretty cumbersome and confusing as your data grows in scope and complexity. So now let's see what the same example looks like using a dictionary, or rather, multiple dictionaries. As I mentioned earlier, dictionaries, along the same lines as lists and tuples, can contain other data structures like lists, tuples, and yes, dictionaries. So first, let's recreate our students list here as a dictionary. So in a new code cell, I'll define a variable called students dictionary, and then my first pair of curly braces, and then my first key will just be the name of our first student, Alice Doe. So then I'll follow that with a colon, and then for the value, I'll actually use another dictionary. So another pair of curly braces, and then for the first key here, I'll just use age, and then a colon, and then Alice's age, which is 20. And then for the second key, I'll type grades, and then a colon, and then I'll just copy and paste that list containing Alice's grades. And then a comma after this key value pair, and then I'll simply copy and paste this first key value pair so I can replicate the steps for Bob and Todd. So now I'll copy and paste Bob Smith, and Bob is 22, and then I'll copy and paste his grades. And finally, we'll account for Todd, who's 21. And Todd probably wishes I'd copy and paste someone else's grades over his, but too bad. Okay, so let's run that. And now, with our dictionary set up, let's see how we might go about retrieving Todd's grade on that second assignment, just like we did with the students list. Now, fetching items from a nested dictionary works just like fetching items from nested lists and tuples. You just add an extra set of brackets after the first pair containing the key of the item you're looking for, as opposed to the index for lists and tuples, of course. So first, let's grab the dictionary containing just Todd's information. So in a new cell, I'll say students dictionary, and then a pair of brackets, and then inside of those, I'll just type Todd, and then I'll run that cell to make sure we're on the right track. And there's the dictionary that pertains specifically to Todd. So now I'll add a second pair of brackets and target the key within that dictionary that pertains to his grades, which, intuitively enough, is just called grades. So now running this again, there are Todd's grades. Now finally, because his grades are contained within a list, I'll actually have to access that second grade using list indexing. So that second grade is at index 1, so now after grades here, I'll just add another pair of brackets, and then the number 1, the index for that grade we're targeting, inside of those, and then running our cell one more time. There's Todd's shining moment, his highest grade, which happened to be on assignment 2. Very cool. So even though this data structure involving different types of information about students is somewhat more complex than the ones we've seen so far, dictionaries made working with it relatively straightforward and intuitive. And that's why dictionaries, like lists and to a somewhat lesser extent tuples, are heavily used in data analysis with Python. Now, it's important to keep in mind that all of these data structures have their place, and there are different scenarios when each is appropriate. While dictionaries are great at making sense of somewhat complex data structures like we see here, especially when it makes intuitive sense for that data to be organized as key value pairs, lists are often the best choice for simple, lists of values, while tuples can be used as an alternative to lists when you have a set of values that you don't want to be changed later on. All right, so since you're clearly still watching, major congrats on making it this far. You now know just enough Python to be dangerous, specifically when it comes to using libraries like Pandas to analyze data. And to that, keep an eye out for another video on my channel dealing with just that very soon. Or, if you really want to dive deep, you can check out my complete Python/Pandas data analysis bootcamp on Udemy. Either way, the best way to make sure all the stuff you just learned sticks is to do something useful, or at least interesting, with it. Best of luck with that, and I'll see you next time.